Hello and welcome to another video. Today we're going to be continuing on with the Typescript line 75 and we're going to be doing construct binary tree from preorder and inorder traversal. In this problem you're given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree, and you want to construct and return the tree. So let's kind of remind ourselves what a preorder traversal is first of all. So a preorder traversal is you go to the root. So actually, let's write over here. So preorder, you go to the root, you go left, and you go right. And then for inorder, you go left, right, root. So let's kind of walk through that for both of these. So first of all, for the preorder for this tree, you would have this, which is the root. Then you go left, so 9. Then you go right. And now we're here, so we get that value here. Then we go left. And then we go right. Okay. And now let's go through the inorder traversal in another color. So for inorder, it's left, right, root. So as long as you can go left, you want to go left. So we start here, but because this has a left, we're going to go left first. So then we go here. This doesn't have a left, so we're going to put in that node. Then we come back over here. So we put in the 3. Then we go right. But once again, we want to go left before we take the root. So we go left here, so 15. Then we come back to the 20. And then right, we go 7. And the reason it's called inorder is because if this was like a binary search tree, then an inorder traversal would give you all of the values. The values would actually be ascending. It doesn't work in a binary tree, but in a binary search tree, they would be like from the smallest to the biggest value, and you can try that out if you want to. But essentially, we need to build this tree from these nodes. So let's actually try another tree that's a little bit bigger. And yeah, like the output is just showing building the tree. So that's not really, like, these examples are not the best, because they don't really do anything, right? They just build a tree. So let's just build a tree, and we are actually going to use a binary search tree just to make it clearer. So let's just say we have like 5, or actually let's just pick some bigger value, 9. We have like maybe 8, not 8, like 6. We have 4. We have 8 over here. Maybe we have like 7 or something. So that's 1, and then we also can have like 1. That's big enough. Now over here we can have like 12, 15, 25, 35, let's say. Something like that. Let's just say we have a tree like this, right? This is pretty reasonable. So let's do the pre and inorder traversal for this one. So let's start with the preorder. So we're going to start the root, remember? Then we go left, and we take that root. Then, so once we go left and we take the root, we want to keep going left, right, and taking the root essentially. So we would go left, and take that root. Then we would go left, and take that root. Okay, now we would recurse back up here. This. Now we want to go right. And we want to take the root value first, right? So we're going to take the root value, then we go left, 7. Then we are going to, so we came down here, now we're going to recurse, 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 and now we just take these values, right, obviously, because that's the only thing we can do. So 12, 15, 25, 35. Now what I actually want to do is I want to just copy this out. And then I want to kind of go back. So we have our tree again, ideally, and we want to have the traversal over here. So we can do that like this. So we have the preorder. Now let's do the inorder. Let's actually use another color for that. So for the inorder, you want to go left as far as you can, and you don't take the value until you go all the way to the left. So here we start the root, Then we go left, we go left, we go left. Okay, now we're going to have a 1. Now we recurse back up to the 4. Go to the 4. Now for the 6, we take the 6. So remember, it's left, root, right. So then we go to the 8. But this 8 has a left value, so we're going to recurse down here first. Then we're going to 7, recurse back up, 8. Then we recurse back up to the 6, recurse back up to the 9. And then finally, obviously, these values are just going to be, we can't go left, so it's just going to be 12, 15, 25. Okay, there we go. So you can see for these, this in order is actually in order, right? So this is like the in order value. That's what I was saying. If you had a binary search tree, this would make it kind of clear as to why this is. While this pre-order is not in order. Okay, so now we have to kind of figure out, let's actually get rid of all these things. Now we have to kind of figure out, and like I said, hopefully I did the pre-order correct. It would be very sad if I didn't, because that would make the problem kind of weird. How do we actually build up this tree from these two arrays? So we're actually going to just have these two arrays, and we are going to copy them down here, because this is what we have. We don't actually have the tree. And we need to figure out, like, how we actually do that, right, for the pre-order. So by the way, if you look, just real quick, we're going to start at the pre-order, and we're going to go node by node. Let's just do a different color. But actually, let me actually copy this pre-order up here just to kind of show you. But we're going to use it. But if you look, if we go node by node, the first node of the tree you want to be the root, right? Then the second node of the tree is going to be the root left. And then the third node of the tree is going to be like here. But the problem is you don't really know, like let's say you have 9 and then you have a 6. Well, this isn't necessarily a binary search tree. So like you don't know if the 6 is, you know that you do want the 6 to be connected to the 9 somewhere, but you don't know if it's like here or it's like here. You don't really know, right? And so how would we know? And the way to know that is going to be by using the in order. So if we actually scroll down and we look, okay, well, we have this 9. We know we want the second value to be 6, right? So we're going to go value by value. We know we want the second value to be 6, but like, how do we even know where that 6 is, right? Like, is it in the left or right? And that's where you use the in order. So if you actually look, let's actually bring this up as well, just to show you. So let's bring this up as well, but then we're going to build up the tree on our own right after this. So let's actually bring this up here. Let's get rid of this 9, and let's actually try to ideally copy this thing and bring it up. Close enough. Okay. And then we can get rid of this, and we can put this in. So there we go. Different color, but that's okay. So when we try to get the 6, we know if we know where the 9 is in the in order, we can just check where the 6 is, right? And also keep in mind, because the pre-order traversal is root, left, right, when we get the left of the root, if we actually look, because we have an in order traversal, when we're building the left subtree, this is the left subtree. These are all the nodes, right? So if you actually look, this is the left subtree. We don't know the exact order of them, but we know like where it is. Similarly, the right subtree is all these nodes, as you can see from there. And that's always going to be the case. So whenever you build up a root, we're going to use this in order to figure out like what are the nodes that are in the left subtree, what are the nodes that are in the right subtree, and that way we know as we go node by node where those nodes actually go, because the in order kind of tells us the bounds for the left and right subtree. And similarly, let's say we build a root over here, right? If there's nothing to the left, that means the left of this has to be null. And you can see that, right? So this is the leftmost node. So we just simply lower our bounds for the left and right subtree of each root until our subtrees are basically nothing. And then we put in null nodes, and we just go node by node and by node to build them up. So that's kind of the steps. Now we are also going to want to, so it does tell you in the problem that all of these nodes are unique. It's not always going to be the case for a binary tree, but in this problem they are. So let's say you use a value like 6. You want to know really quickly, like, where is 6 in this in order array? So we're actually going to, instead of using an array, we're actually going to use a set to get the index, or not a set, a hash map. So we're just going to take this array and just hash out every single value to its index. That way we could be like, okay, we need a 6. Where is it right away? Because we don't want to be like, we don't want to be going through this every single time to get an index. That's why we're going to use a hash map for that part. But now we know enough to like start building up this tree. So let's actually just use these arrays and start building out the tree. So this is our preorder, and this is our inorder. So we start with the first node, and we say, okay, so our root is going to be 9. We know that for sure. Now, where is 9 in this array? And also, keep in mind, our left and right bounds, I guess we can draw it like this. Our left and right bounds initially are going to be the entire inorder. So our like initial parameters for the left and the right are just going to be like this whole thing, right? But as we build nodes, we have to lower our left and right bounds to make sure that we know like what's in our left and right subtree. So when we find 9 in this array, we're going to say, okay, so we have a 9 here. Now let's build up the left side. And to build up the left side, the left subtree is going to be nodes from here to here, right? Because our starting left is going to be like 0 and our starting right is going to be over here. But then as you build, as you choose a root node, then you have to modify your left and your right accordingly, right? So we can write that down. So when we pick a root, left subtree will have bounds the old left, whatever that was, left, and then the index -1, right? So if this was your root, then your left subtree is going to obviously have the rightmost index of index -1, and similarly the right subtree will have bounds index +1 and then right. And we can just simply check, like for example here, if the right was over here, let's say, or whatever, we can simply just say like, yeah, so the left is going to be over here, and then the left will be greater than the right, right? So if we have some like left that's greater than the right, then we know it's null. And also if we have something out of bounds, then we know it's null. But anyway, let's go through this. So like I said, our original left and right indices will be over here. They'll start over here. But now that we picked a root here, let's say, for the left subtree, our indices will be here and here. So when we recurse, and then we just take the next node, right? So we take the next node and we say, okay, well, we know like this is the order we want to build our nodes, but we just don't know where they are. So when we're building the left subtree, there's a 6 somewhere in here, but we don't know like where it is. And so, but we do know that because we're going to build the left subtree, then the right subtree, right? So we're going to say like build a root, then traverse left, and make that left subtree, and then traverse right, because our preorder traversal is root left right. So we want to follow that same logic. Similarly, if you had a post-order traversal, it's like left right root. So you would go backwards, and then you would want to go like root right left. You want to have the same order as you do in your actual traversal. So we put in a 6 here. And now, similarly, the same thing, we're going to go left again. We're always going root left right, right? So, but these were our old bounds. They were the 1 and the 8. So for the 6, our bounds are going to be, at least for the left side of the 6, these were our old bounds. For the left side of the 6, our bounds are actually going to be over here and over here, right? Those are going to be our bounds because the 6 is here, so our left has to be, our old bounds, but now our left has to be below the 6. Okay, so then we recurse again. Now we say, we want a 4. Remember, we're going left first, so we put in a 4. And now what are our bounds for the 4? So they used to be this, but now, once we chose the 4 as our index, our bounds will actually be this. They will be both on 1. The left and the right will be 1. So then we recurse. We say, okay, 1. Now, remember, we go left and right again. Now the left bound for the 1 will be this. So the right bound will still be 1. Actually, sorry. No, the left bound will be over here. The left bound will be out of bounds. And the right bound will be the old one that it was. No. Actually, no. Okay, I keep screwing that up. Okay, so if the left and the right are 0, right? If the left and the right are 0, if we take a look, the left subtree will have bounds left and index -1, so it'll be 0 and then 0 -1. There we go. Which will be 0 and -1, and obviously you can't have that because your left has to be smaller than your right. So when we go left here, we're going to say, okay, where our left and right, our left is bigger than our right, so this is going to be null. Now for the right side of this one, remember we had the 4 and both of our bounds were over here. The right side is going to be kind of the same issue. So the right side will have index plus 1, right? So it'll be 1, 0. And then that's also the left is greater than the right, so that's null as well. Okay. So now we recurse back to our 4. And it is kind of hard to draw this in the picture, but the starting bounds for our 4, remember where they were here and here, right? But now we need the right side of the 4. So the right side of the 4, if we take a look, will be index plus 1 and right. And so the right was over here, but index plus 1 will be over here. So it'll be like 2, 1, which is also out of bounds, right? The left can't be greater than the right. So for the 4, this will also be null. Okay, now we come back to the 6, and these were our old bounds for the 6. And now we need to do the right side. So the bounds for the 6 right side will be, I think they will be like 7 and 8, right? Because when we made the 9, the bounds for the 6 were actually this over here. So the right side bounds for the 6 will be 7 and 8. And so basically what that means is we will go over here and we actually, so we used the 1 already. So now we are on this 8. So this is a valid index. So for the 6, the right value for the 6 will be an 8, right? Because we're taking the right value. And that's how we know, like, we know that the 8 comes before the 7 because we're literally following the preorder. So we will put an 8 here. And now we need the left side for the 8. So the left side for the 8 is going to be this 7, right? Yeah. So the left side for this 8 will be 7. And now, obviously, because both of these values are on the 7, when we get the left for the 7, it'll be out of bounds. And when we get the right for the 7, it will also be out of bounds. So we're done with that. Now we recurse back up to 8. Then we recurse back up to 6. Then we recurse back up to 9. And so for the 9, now we do the left side. So when we originally did the 9, remember, that was our original root node, right? So the left and right values were here. But now what are the boundaries for the right side of 9? Well, it's going to be the node right after 9 and then the old ending node. So it's going to be this part here. So now, once again, we need to use this preorder to figure out, well, what value actually goes first, right? It can be any one of these, but how do we know? We follow the preorder, and it's going to be 12. Okay, so now we use the 12, and then we try to get the left side for the 12. So as you can see for the 12, there is nothing to the left of it, right? Because essentially this right will go out of bounds. So there's nothing to the left of the 12. Okay, well, what about to the right of the 12? So to the right of the 12 is this whole thing. So it's going to be this whole thing here, right? These are the bounds to the right of the 12. So which value do we want first? Well, it's the 15. Then we go to the next value. And for the 15, there is no left again, right? Because our leftmost value for the 15 is here. So essentially this will be out of bounds. So then we go to the next value and we say, okay, what's to the right of 15? Well, to the right of 15, these are the bounds, 25 or 35. Well, which value do we put in first? We're just following the preorder, 25. And then once we put in 25, what's our left of the 25? Well, there's nothing once again, right? Because we've already used the 15. So this is our left bound, this is our right bound. So essentially it'll be something like this, where our right bound is over here, which will make it null. And then finally, we want to go to the 35, and we use that as well. And then once we go to the 35, our left and our right are both on, or starting anyway, they were both on 35. So when you go right, they will both be null because the left will be greater than the right. And then if you go left, then the right will be less than the left. So it's the same thing. The left will be greater than the right in both cases. So now we went through every single value. And if we actually take this tree, hopefully I can do that. Let's see here. Might be able to copy some text, which will be fine. Okay, close enough. So you can see that like when we built this tree, if we look, so it's 9, and this is pretty much the exact same tree that we had. It's a little hard to see, but there we go. So you can see like essentially you just follow the preorder in terms of like which node do I want, and you just keep setting new boundaries in your Inorder. I know it's kind of hard to draw in the picture, but it's going to be a lot easier to see in the code. And then as long as your boundaries actually have values, you know which value to use because you just follow the preorder. And you keep doing that until you run out of nodes. So that's pretty much our solution. So now we can code it up. And like I said, you can do this using a post order and Inorder, and you just have to change your logic a little bit to figure out like what's the order for post order. I'm going to need to follow that. And I need to make sure that my root is my first node, so I would traverse the post order backwards. Okay, so the first thing we are going to do is, like I said, for Inorder, we're actually going to need to find the index of the current number we used in O of 1 time. And because every number is unique, we're just going to make a dictionary for that, or an object in Typescript. So we can use a record. It's going to take a number and a number because it will essentially be a number and its index. So it'll be number, and we're going to set it equal to an empty object. And now we are going to, we also need to store the index in the preorder that we're currently on, right? The next available number that we're using. So we could just say let pre, and we'll start at index 0. Then we want to loop through every single number in Inorder, so we can just say let I equals 0, I is less than Inorder dot length, I plus plus, right? We want to loop through them, and we want to save the index of every single number so we can get it in big O of 1 time, because we're going to need to use it a lot. So that was going to speed it up. So essentially locations Inorder I equals I, we're just saving. So the key will be the number, and then the value will be the index, so we can get it really quickly. So once we use a number in preorder, we can figure out where it is in Inorder in O of 1 time. Okay, now we're going to make a helper function. So we're going to call it traverse. And it's going to take a left, right? This is the left bound number, and then it's going to take the right, which is also a number. And then it will either return a tree node, or it will return null if the left and the right, if something's out of bounds. So first thing, we're going to check if left is greater than right. That means we don't have like any valid things to pick, right? So if like left is, if the index of the left is 1 and right is like 0 or something, we're out of bounds. Kind of like a binary search, basically the same thing, right? If left is greater than right, we don't have any possible numbers we can pick. There's nothing valid. Okay, that's number 1. Then we are going to actually make a node. And what node do we want? Well, we want to actually pick the node that is at index pre in preorder, right? We're essentially building up nodes in the same order as that preorder array. So we can just say const root equals new tree node. And it turns out you don't really need to make sure that your preorder is out of bounds, because when your preorder is out of bounds, this will always be true, so you'll always get null nodes. So it's kind of like a redundant check. You don't need to make sure that your preorder is in bounds. So we can say preorder, pre, essentially whatever the index is there, let's get that value, let's build up a root. Now remember, since our preorder traversal is root left right, now we're going to want to go left first, but before we do that, we actually want to increment this preorder, and we can simply do that like this, in place. So essentially we're saying, let's get that index, let's get the value, and then let's increment it in place. Now we want to go left, so we're going to say root.left equals traverse left. And remember, the bounds when you go left, right, in the picture, as you can see, so if you go left, the bounds will be left index -1, and then when you go right, it'll be index +1 right. So when we go left, we want to say, okay, well, let's take the location of the value, wherever that was, and when you go left, the right boundary will be the one right before that, right? So if we have an array like, if our Inorder is like 1, 2, 3, 4, 5, so on, and our old left bound was this one, and our right bound was over here, let's say, when we pick the 5, our new left bound will be this index, and then our old left bound stays the same. Similarly, when we take the right side, our new left bound will be the one right after it, and then our right bound stays the same. So it's kind of similar to like a binary search. Okay. And now we do the same thing for the right. So we say root.right equals traverse. And then the new left will be locations root.val. And then it's going to be +1. And like I said, so in every single one, we are using the set twice. So if we didn't have this, this would be O of n times. So then we'd have an n² solution, which wouldn't be good. That's why, or the hash map is useful here. And then finally, we can return the root. Oh yeah, so we need an equals here. And finally, so now that we have this helper function that will essentially say, okay, if we don't have any valid nodes, let's return null. Let's build the route wherever we currently are in the preorder traversal. Then let's go left, then let's go right, and modify the left and the right bound appropriately, and then let's return the route. Now we actually need to call it, right? So we need to say return traverse. And this first traversal will return the root of the whole tree. So the first bounds we want are just going to be, the left is going to be 0, and then the right bound is going to be, you can use Inorder or Preorder because they should be the same length. Essentially, the right bound is going to be the very last index in the array, right? You can use any value in the beginning. Okay, and then let's try that. And you can see it's pretty effective. But yeah, this problem is quite weird. And I would say that if you do think you know this one, then you should do the construct binary tree from post order and inorder traversal. It's very similar to this. So if you think you get this one, then do that one and try to kind of do all the steps that I showed you, like figure out what's the order for the post order, which order should I recurse, how do I make sure my left and my right indices are updated correctly to make sure I'm using my values. But yeah, let's actually go through the time and space real quick as well before we end here. So for the time, so for this set build, that's already n, right? But you're going to notice the set build doesn't actually cost us anything in terms of O, time and space, and we're going to see that in a second. But essentially, yeah, for this, or not set, I keep calling it a set, it's actually like a hash map or an object. That's going to be O of n time, where n is the length of preorder, and the length of preorder and inorder is exactly the same, so whatever you want to use there. And so traverse is going to traverse the entire preorder array, so that's going to be O of n. But also, now for the space, so yeah, this is going to be basically O of 1 in one traversal, but then it's going to recurse, right? So it's going to end up building out this whole tree by traversing the array. So that's going to be O of n for this function here. Now for the space, so building out this hash map is O of n because we essentially built like a new hash map that's the length of one of these. But also, worst case scenario for traverse, as always for all these tree problems, if your tree ends up like this, right, then your recursive call stack will be O of n as well. So if you factor in the recursion, actually making the set doesn't cost you anything in complexity, because this traverse can be worst case space O of n as well. Because if you have a completely unbalanced tree, it will be O of n. But on average, it will be log n. So then you could say, like, on average, building this hash map hurts, but worst case, it does not. And yeah, I think that's going to be it for this problem. But yeah, if we didn't have this, like I said, if we didn't have this object, then getting this index of whatever value we just picked in preorder, getting that in inorder is going to be O of n. So then we'd have an n squared solution, and we would still have worst case O of n, average case log n. So this is like I guess, a better compromise for a solution. But yeah, that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.